So we're going to begin, and please feel free to interrupt me if you want. I'm recording. I could always pause and go back and continue recording. So, what is an exponential function? You don't have to copy this down, but please pay attention. An exponential function has a variable in the exponent. So here's an exponential function, y equals 2 to the x. What makes it exponential is that x is in the exponent position. Okay. What about this next question? What does the exponential growth function look like? Okay, we actually did this, or we talked about this parent graph before spring break, where you kept doubling your money, right? And it didn't seem that much, but pretty much from left to right, it seems like it's not growing, and then all of a sudden it grows really quick. Okay, so how about this? On your Chromebooks right now, go to desmos.com and type in y equals 2 to the x, and let's get a precise um, visual of what that looks like. So go to desmos.com, type in y equals 2 to the x. So hopefully you already have this pulled up, and as you could see, y equals 2 to the x. Let me get this out of the way since we actually have it graphed right there. Y equals 2 to the x. What happens is from left to right, it grows away from the asymptote. Okay. In this case, the asymptote is the horizontal line y equals 0. Okay. So from left to right, it grows away from the asymptote. What do I mean by it grows away from the asymptote? If you look at that distance from here to there, and from left to right, look at that distance, look at that distance, it keeps growing away from the asymptote. So from left to right, it's a growth function. So visually, you could tell if it's a growth or a decay function by looking at the graph, the way you read a sentence from left to right. And it is growing away from your asymptote. That's a growth function. Algebraically, you could tell if it's a growth or a decay function by looking at this base. If the base is greater than 1, it's going to cause it to grow from left to right. It'll grow away from the asymptote. If the base is a fraction or decimal less than 1, it's going to decay towards the asymptote from left to right. So it'd be something like that, a decay function, if that would have been a 1/2. And we'll get to some of those examples in a bit. So right now, I want you to understand that the base tells you if it's a growth or a decay function, if it from left to right grows away from your asymptote or it decays towards your asymptote. So we're going to eventually understand what this looks like even without Desmos, all right? But right now, you should be on Desmos, and you should have the parent graph y equals 2 to the x on there. And what I would like you to do is to compare y equals 2 to the x to y equals 3 times 2 to the x. What I want to do is type in a 3 right in front of there, okay? So on Desmos is what I would like you to do. Let's do both the original y equals 2 to the x, hit enter, and then as a separate function, type in y equals, throw in the a value of 3 instead of 1. Throw in the a value of 3 and everything else the same. And go ahead and do that. And then we'll talk about what happens by us putting the a value of 3 right in front of there. What happens to the original parent graph? So hopefully everybody already typed this into Desmos, and you'll be able to compare the original parent graph to this new graph. Okay. Um, on my Desmos, it graphed the original one in red, and it graphed the next one with the a value of 3 in blue. So they're still both growth functions because this value is greater than 1, that value is greater than 1, and it makes total logical sense. Anything times 2 makes it grow. 5 times 2 grows to 10. 3 times 2 grows to 6. So anything with the 2 right there is going to be a growth function. So both of them from left to right, they grow away from the asymptote. They grow away from the asymptote. But when you throw in the a value of 3, that causes a vertical stretch, okay? So the original one had the y-intercept at 0, 1, and if you want to put that 3 in front of there, that's going to cause that y value to grow by 3. So it gets vertically stretched by that a value of 3, okay? Now, if there would have been like a 5, it would have gotten stretched all the way to 5. If it would have been a value of 8, it would have been stretched all the way to 8, right? So that's what the a value it does. It causes a stretch or a compression. And I do that by, or demonstrate that by doing all of these functions. You don't have to do it on Desmos right now on your Chromebook, but you could just watch. So if we compare all of these, obviously just focusing in on the y-intercept, the parent graph had the a value of 1, uh, which means that it has the y-intercept at 1, okay? And that's because there is no h or k shift. But if you throw in the a value of 2, it gets vertically stretched to 2. Throw in the a value of 4, it gets vertically stretched to 4. The a value of 6 gets vertically stretched to 6. And likewise, if we didn't have a number greater than 1, it wouldn't be a vertical stretch, it'd be an actual compression. So on this next slide, I'm going to show you comparing the original parent graph with the a value of 1/2, which is not going to be a vertical stretch, it's going to be a vertical compression. So check this out. Y equals 2 to the x would be the red one. But when you put an a value of 1/2, it's going to cause a compression. So if you take that y-intercept of 1 and then multiply it by 1/2, it actually gets compressed, right? As opposed to stretched. So if the a value was 3, it would get stretched up to 3. But the a value is 1/2, so it gets compressed to 1/2. Do we understand how the a value affects the graph? Yes? 2 people. Okay, let's move on. What if you put a negative sign out there as your a value, right? Go ahead and graph that on Desmos. Compare the original parent graph with y equals negative parentheses 2 to the x power. Not negative 2 in parentheses, negative on the outside of the parentheses. In other words, if your a value is negative 1, what happens? It's kind of like the parabola. If the a value is negative, it reflects over the x-axis. It opens down. And then if you actually have a numeric value, that causes a stretch or a compression. So all the stuff that we're learning on exponential growth and decay functions, we kind of already know from parabolas. But again, right now I'd like you to compare the original parent graph, y equals 2 to the x, to y equals negative on the outside, and then parentheses 2 to the x. That's just going to cause a reflection over the x-axis. And then after that, I would like you to put maybe a value of negative 4. So not only does it reflect over the x-axis, but it also gets vertically stretched by 4. Or right here, not only does it reflect over the x-axis, it gets vertically stretched by 6. So I guess you could type these in on Desmos, or you could just pay attention right now. You could see that the original red parent graph is right here. But when you put a negative, it's going to be the blue one now. It gets reflected over the x-axis. So whatever points this guy had, it gets reflected over the x-axis. So this point right here at 2, 4 is now going to be down here at 2, negative 4. It just gets reflected over the x-axis, right? Or he could have said the point 0, 1 gets reflected over the x-axis to 0, negative 1. So we all understand that the a value, if it's negative, it gets reflected over the x-axis. Then on top of that, if your a value is further away from 0, that's a vertical stretch. If your a value is closer to 0, it's a vertical compression. So this one opens down, that's the blue one. If you go to this next one, the green one, not only does it open down, but it gets vertically stretched by 4. So not only does this green one open down, but instead of having the coordinate 0, negative 1, if you stretch it by 4, it'd be 0, negative 4. Okay. Likewise, opening down, vertically stretched by 6, opening down, vertically stretched by 6. There's this exponential growth function that passes through 0, negative 6. So I hope this helps you understand how the a value affects your exponential growth or decay function. Dotted line, in a nutshell or in summary, the a value tells you if it reflects over the x-axis. So if you have a negative sign, you're going to say it reflects over the x-axis. It's going to open down instead of up. And also if it gets vertically stretched or compressed, if the closer it is to 0, the more compressed it is. The more compressed it is, like a fraction or decimal that's less than 1, that's a compression. But if it's further away from 0, like a 2, a 3, or even a 1.5, if it's greater than 1, the further away it is from 0, it's a vertical stretch. Okay, so the a value tells you if it gets reflected and if it gets vertically stretched or compressed. Again, bigger than 1 is a stretch, a fraction or decimal less than 1, it's a compression. So now on Desmos, I would like you to compare y equals the a value of 1/2, which causes a slight compression. But then I want you to just throw in the k value of -3. So put a -3 at the very end, not a -3 up on the exponent, but a -3 at the very end. Okay. So compare those two on Desmos. So this is what I want you to type in, those two, and then put in that -3. That way we could understand how that k value changes it. Now we already know that from the parent graph to this guy, it's going to get vertically compressed by 1/2. So just a quick sketch here. If my original one looks like this, um, my new one is now still gonna go up, but it's gonna open up a little slower. Okay, so the red one opens up faster, the blue one or the black one opens up a little slower. Now, this next one has a k value of -3, and I hope we remember from before spring break that that k value ultimately gives you your asymptote. Your asymptote will be y equals that k value, -3. So just by knowing this stuff, if you look at a multiple choice question, you'll be able to identify the correct one. Now, we already know it's growing from left to right. It's going to grow away from the asymptote. We know that the asymptote's at -3. So -1, -2, -3. So that's a horizontal asymptote. And we know from left to right, it's going to grow away from the asymptote in a positive direction. So we already have an idea that it's going to look like this, right? If you want to be more specific, you could actually find the y-intercept by setting x equal to 0 and solving. 2 to the 0 is 1. 1 times half is half. Half minus 3, that'd be a -2.5. So it would cross at -2.5. So this isn't exactly accurate. But let's compare them on Desmos, all three. Like I said, yours might have different colors. Mine, the parent graph is in red, regular, y equals 2 to the x. What happens if I put an a value of 1/2? It gets vertically compressed, it gets kind of smashed, right? Vertically compressed by half. And then the k value of -3 causes a shift 3 units down. You guys with me? Okay. So these are the notes that are going to tell you pretty much everything, right? Um, we need to really get comfortable with this format. Y equals a. The a value tells you if it gets reflected over the x-axis, if it gets vertically stretched or compressed. The b value tells you if it's going to be a growth function or a decay function. If the b value is greater than 1, it's growth, even if it's a decimal or a fraction. If that fraction or decimal is greater than 1, it's going to cause it to grow. From left to right, it's going to grow away from the asymptote. And if for some reason it's less than 1, it'd be a compression. From left to right, it'll, not a compression, a decay function. From left to right, it'll decay towards the asymptote. The h and k are simply shifts, right? You shift h units either left or right, but you think opposite on h, and the k is your asymptote, which is ultimately your shift up and down. So let's jot down some notes here. The a value tells you if it reflects over the x-axis and if it gets vertically stretched or compressed. Now, you may not have different colors, different colored pen or pencils, so you may have to just like circle this info right there that talks about a, and then you can move on to the b value. What does the b tell you? The b tells you if it's a growth or a decay function, if it's a growth or the decay factor. Okay, so all these notes right here are about b, and you don't have to copy this down word for word. You could read it, understand it, write it in your own words. So the b value tells you if it's growing away from left to right. If it grows away, that's because it's greater than 1. Or if it decays, that'd be a value less than 1, between 0 and 1. Then it's a decay function. It'll infinitely approach your asymptote from left to right. What about your k value? We said that the k value tells you your shift up or down, but it also, more importantly, automatically gives you the asymptote, which will always be the horizontal line y equals whatever that k value is. So all of this stuff comes from k. Okay. And what about the H? Well, the H, there's a couple of things to say. You got to think opposite of what you see. So if you see a -3, your H value is actually +3. Think opposite of what you see. And that ultimately is your shift left or right. Okay. The K value is your shift up or down. The H values are shift left or right. And again, as you guys copy this stuff down, you should be thinking, wait a minute, didn't I already take these notes? Yes, you did. Back when we did parabolas, it was the same exact stuff. So here's a picture of the wall. And this my Algebra 1 classes are actually learning this stuff right now. That's why it's on the wall. But we had this back when we did parabolas. Vertex form, we know that the A value, if it's negative, it reflected over the x-axis. We know that if it's a value between 0 and 1, it's a vertical compression. If it's a value bigger than 1, it's a stretch. We know that to find the vertex, you got to do H and K, but you think opposite of what you see on H and you take K for what it is, and that's your vertex. It's all the same exact stuff as what you're copying down right here. Again, the A value tells you if it's above or below, if it opens up or down, above or below the asymptote. The B value is the growth or the decay factor. And the H is the left and right shift, but think opposite of what you see. And the K is the up or down shift. You take that for what it is. So I'm going to pause it right now, give you guys time to jot this down, then we'll move on. So we just had an excellent question. How do we find the y-intercept? And if you look at the wall over here, whoops, and you go to y-intercept, for the y-intercept of any graph, it doesn't have to be a parabola or a line or exponential growth function or decay function. For any function, any graph, if you want to find out where it crosses the y-axis, all you have to do is set x equal to 0 and solve. So you're going to put x being 0 and you solve for y, and that'll tell you where it crosses the y-axis. Okay. So technically, whatever function you have, whether it's a growth or decay function, if you want to know where that growth or decay function crosses the y-axis, all you have to do is set x equal to 0 and then solve it. Now, if you didn't have an h, it's really easy because anything to the power of 0 becomes 1, then multiply that by whatever number you have out here, and then add or subtract whatever you have at the end, and that'll tell you where it crosses the y-axis. And we'll do a couple of examples of these in a bit. So these notes are great to know everything that you need to know about graphing growth or decay functions. But you know what? I still haven't given you a solid step-by-step instruction on or method on how to graph growth or decay functions. So let's do that. Step one is to identify H and K and then ignore them. Okay. Step two is to set up an XY table with consecutive integer inputs. And step three is to get your coordinates that you get by plugging in these numbers and getting out answers, ignoring H and K, and then plotting them on a graph. And then at the very end, you shift the coordinates, you shift the points according to H and K. So let's not write down these instructions yet. Let's actually see an example of this first, and then you could see them in action, and then it'll make more sense. So we got this paper before break. Some of us just got it right now because you couldn't find it. Um, we already have a lot of info right here, and we should have graphed this original parent graph already. But let's jump to this one, and let's use these steps right here. Step one says identify H and K. So could you guys look at that original graph and tell me what H is? H equals what? Yep, you think opposite of what you see right there. So that'll be H is a +2. How about the K value? What's the K value? -3. Take that for what it is. Perfect. Nice and easy, right? So step one's easy. Identify H and K and then ignore them. Now, when I say ignore them, what I usually do is I box in the function, but I leave the H and K on the outside of the box. Okay, so it's kind of like we're gonna pretend that they're not there, even though they are. Okay, and I'm gonna make a input output table. And by the way, this is step two right here, where step two set up a XY table and use consecutive integer inputs. Okay, so I'm gonna do consecutive integer inputs: -3, -2, -1, 0, 1, 2, 3. And you could do as far as you want or as many numbers as you want. And now I'm going to actually plug in this easy number 0 into this, but ignoring h and k. So that would be super easy. When you plug in 0 right there, 4 to the 0, anything to the 0 is 1. And then 1 times the a value of negative 1/2, that will be negative 1/2. Yay? Now, ignoring h and k, I could get my next output by making it either grow or decay. First of all, is it going to grow or decay? Grow, because the base is greater than 1. It's 4. When you multiply anything by 4, it grows. 4 times 5, 5 times 4, it grows to 20. So the base being 4 is going to cause a growth. So I need to cause this output to grow by 4. So you would simply go negative 1/2 times 4, and that'll give you your next output. Your next output would be negative 2. And then you're going to make this grow by 4, and that'll be negative 8. And then you're going to make this grow by 4, and it'll be negative 32, which you're not even going to use because it's only a 10 by 10 graph. But you get the idea? So again, the only reason why you're able to make this grow by 4 is because you have consecutive integer inputs there in order. If you just put random numbers for x, this would not be able to be done. Now, if it is growing by 4, going this way, then backwards, it's dividing by 4, okay? Which also means multiplying by 1/4. Instead of dividing by 4, it's multiplying by 1/4. So if you say 1/4 of negative 32, that gives you negative 38. 1/4 of that is negative 2. 1/4 of that is negative 1/2. 1/4 of this would be multiplying negative 1/2 times 1/4. That would be negative 1/8. Then multiplying by 1/4 again would be negative 1 over 32. And clearly it's already so small that you're not going to be able to draw the difference. So what we're going to do here is graph these points. And again, these points are not to the final graph. These points are just to this boxed in red portion of it. I'm ignoring h and k for a moment. Okay. So if I actually plot these in blue, let's go to the first one, 0 and negative half. 0 and then halfway down would be right there. Then you move on to 1, negative 2. 1, negative 2 would be right there. Move on to 2, negative 8. 2 on the x, negative 8 on the y would be right there. If you tried 3 and negative 32, that's way off the graph. So forget it. I'm not going to worry about that last one. Now, what happens as you go to the negatives on the x? Negative 1 and negative 1/8. Negative 1 and negative 1/8, it's way smaller than negative 1/2. So negative 1 and negative 1/8, it's even closer to the x-axis. So you get the idea that the next one's going to be even closer, even closer, even closer, but you can't physically draw the difference. It looks like the dots are touching the asymptote. In this case, the asymptote y equals 0. But like I said, this graph right here is not your final graph. This graph is of this, ignoring h and k. Okay. Now, what does that mean? We need to actually include h and k. And h, we said, was positive 2, which ultimately produces a shift 2 units to the right. And the k value being negative 3, which ultimately produces 3 units shifted down. Okay. You could start by writing down your asymptote y equals that k value of negative 3, which means that it would have the horizontal line at negative 1, negative 2, negative 3 right here. And this would be your asymptote. And if you understand that the original one was here and it has to shift 3 units down, your new asymptote's going to be right here, right? But the reality is all of these points are going to shift 2 units to the right and 3 units down. So it's kind of silly to move this one 2 to the right and 3 down. You're going to end up right here. It's just going to be at the asymptote. You're going to draw it like if it's touching, even though you know it never actually touches, it just infinitely approaches. But how about like this nice point? You could go 2 to the right and 1, 2, 3 down and put a dot right there. Now I'm going to graph this in red. And then I want to take this guy and go 2 to the right and 3 down. I'll be 1 unit off. And of course, all of these dots that were right here on this asymptote got shifted 2 to the right and 3 down. So they would still be 2 to the right and 3 down would be right here. This guy right here that was at the halfway point gets 2 to the right, which is still at the halfway point, and then 3 down, 1, 2, and you're at that halfway point. And then you just connect your dots and you have your final graph. Arrow, we know that it infinitely approaches that asymptote. You draw it like if it's actually touching, even though you know it never actually touches, it just infinitely approaches. So let's go through the steps one more time. Um, Step one, identify H and K, ignore them. I do that by boxing it in, ignoring H and K. I write down H and K. And then I get my coordinates. I use the growth factor to make the answers easier. I mean, you could have technically plugged in a 2, done the math. You would have gotten out a -8. But we are ignoring H and K. So you come up with your points. You graph those points, but of course it doesn't have the H and K. So at the very end, you got to shift according to H and K. Now we did that shift. We did it visually. We moved 2 to the right and 3 down, but you could have done it numerically, algebraically as well. If you say 2 to the right, that's really adding 2 to the X. So this coordinate, you could have added 2 to the X, and that would have given you a 3, and then you could have subtracted 3 from the y, and that would have given you -5. So you could have done the h modification and the k modification, the h shift numerically and the k shift numerically to get your final coordinates 3, -5. And you could get your final coordinate by doing that. If you went to 1, 2, 3, -5, you'd get to that point right there on the final graph. What do you think? I see the excitement in your faces. Okay. So we need to understand this. We need to practice this. On the back side of this worksheet, we do have a lot of practice. So on all of these, I recommend um, identifying H and K. So H is -5. That means you're going to shift 5 to the left. K is -2. That means you're going to shift 2 down. And then ignore H and K, and then make a quick input-output table. Use consecutive integer inputs. Plug in an easy one like 0. And again, we're ignoring H and K. Plugging in 0 right there. Anything to the 0 is 1. 1 times 8. 1 times the A value of 8 is the A value of 8. And then that 8 is going to grow or decay. Decay by 1/4. 8 times 1/4 is 2. And then 2 times 1/4 is 2/4, which reduces down to 1/2. And you already know that it's going to keep getting smaller and smaller infinitely. Now, if you went backwards, if you're dividing by 4 this way, then you're multiplying by 4 this way. So the next one would be 32, but that's going to be off the graph. So you really only need these 3 dots. 0, 8. 0, 8 is right here. 1, 2. 1, 2 is right there. 2 and half. 2 on the x, only halfway up is right there. So this would be the graph of the boxed in portion, but that's ignoring H and K. And we don't really want to ignore H and K. We only wanted to temporarily ignore them. Now we're going to shift 5 to the left and 2 down. Now you could do that by subtracting 5. And if you did subtract 5, that would be a -5. And 2 down, subtract 2 from the y's, that would be a 6. So you'd end up with the location -5 and 6, which would be right there. Okay. What the heck? Give me a second. I think that's it. -5 and 6. Okay. Um, or of course, you could have shifted 5 to the left and 2 down. 5 to the left and 2 down. I think it's easier to shift visually as opposed to numerically, but you could do whatever you feel more comfortable with. So 5 to the left, 1, 2, 3, 4, 5, and 2 down would be right here. And the reality is your asymptote will be at y equals k. So y equals -2 is your asymptote. So -1, -2. This is your asymptote. And this guy, if you shift it 5 to the left and 2 down, that'll be right here, really close to the asymptote. So this is your final graph. You draw it like if it's actually touching, even though it never actually touches, just infinitely approaches. If for some reason you did draw this original first one ignoring H and K, make sure that you put two X's on it so I know that that's not the final graph. All right, I hope this helps. This will be uploaded onto Google Classroom later.